Welcome to your laser training break. Thank you all for joining this webinar session for today. If you have any question during this whole event, you can write your questions directly in the chat function of WebEx. My colleague Iris will answer your question directly. Or if you have any technical questions after this training break, you can write me an email. My email is erding.m@leser.com. Short, we're starting with a little review. In the last laser training break, we talked about the CDTP. This was the cold differential test pressure. The cold differential test pressure ensures that the safety valve opens on the correct set pressure under operating conditions. This means we correct the influence of the temperature on the spring, and we correct the superimposed back pressure that leads to additional spring force here. So the CDTP correction, the cold differential test pressure ensures that the safety valve opens on the correct set pressure under operating conditions. There we'll talk about in the last laser training break. But for today is the topic of tightness. Tightness, there are different definitions of tightness. For example, we are talking about the body tightness. This is the tightness towards to the outside. And we talk about the functional tightness. The functional tightness, here we see the cutaway model of the API valve. The functional tightness is the tightness between the seat and the disc. And functional tightness is for us so important because it prevents the loss of the medium, of the process medium of the safety valve. So if we have an expensive medium and have a very high loss, so it leads to higher cost for the operator of the plant. Or if you have a toxic medium, there is a danger for human life or for the environment. So it is very important to have a tight valve here, a high functional tightness. Basically, we are testing the functional tightness, the seat tightness, with the same medium that was used for the cold differential test pressure setting, the CDTP setting. For example, if you need a UV stamp. But this is not only the basis for selecting the method of seat tightness. We are also must to know the different type of a safety valve. There is different if we have a gas tight safety valve, for example, or we have a non-gas tight safety valve with an open bonnet. There is a different method we have to use there for the seat tightness testing. And also important is not only the type, there is also the design. This means we have open or closed bonnet, or we have a spring-loaded or pilot-operated safety valve. These are, for example, factors to find the right method of the seat tightness. The only international standard where we find a detailed description of the seat tightness method is the API 527. And there stands in a detailed description of this procedure, and there stands, for example, the leakage rate into the regulation API 527. And what this means in detail, we have a look now into the presentation. Here we see again the definitions of tightness. First, we have the body tightness. This is the tightness towards the outside. And we have the functional tightness, and the functional tightness is the tightness between the seat and the disc. Yes, there's a difference between spring-loaded and pilot-operated safety valves. This we learned now on the laser training break in some seconds. In the next slide, there you see the different methods on the left side. For example, we can do the bubble counting methods. We can do the application of test fluid. We can test it with water, or we can test it with steam. It depends, if I mentioned before, on the different design or type. You see on the left picture, there is a gas-tight safety valve with a closed bonnet, and on the right side, there we have a non-gas-tight safety valve with an open bonnet. On the right side, you see again the list of the codes and standards. In the DIN and ISO stands no specific requirements regarding the leakage rate here. The ASME code section 8 with references to the API 527, and in the API 527 there is the international accepted standard for the seed leakage. And yes, there are, for example, the allowed bubbles per minute. And our LESER global standard has also a reference and derived from the API 527 here. What means our LESER global standards? We see a little bit later in this session. Here you see again the differences between the spring-loaded safety valve on the left side and the pilot-operated safety valve on the right side. If we have a higher pressure in a spring-loaded safety valve, we have a lower closing force. And if we have a higher pressure in a spring-loaded safety valve, we have a higher closing force, because we use here the formula, the function of pressure multiplied by the area. And we can say the seat tightness, a safety valve is considered tight if the maximum permissible leakage rate of the applied standard is not exceeded. This is, for example, a small definition of the seat tightness. In the next slide, there we see the different designs of a safety valve. If we do a test with air, the bubble counting methods here, we have to look which different designs we can use. On the right side, there's, for example, a spring-loaded safety valve in a gas-tight design. You can use it with a cap H2 or cap H4. On the left side, there is a design with an open lift device with a H3. There, a little bit be careful. There we need a closed test cap to be used too. This is, yes, the cap H3 is not gas tight. And if we do the bubble counting methods here, then we have to use a closed test cap for this test. And we can also use the bubble counting method for design with open bonnet and a balanced bellow design, because there's a protection of the balanced bellow to the bonnet. Or we use it for a PSV valve on the right side. In the next slide, there we see in detail what means the method of bubble counting. You see on the left side, there is the bubble counting device. It is a transparent vessel filled in with water. We have a defined inner tube diameter, and we have a defined water heat. So we have a defined bubble volume of 0.295 square centimeter here. And you see on the top, there is connected a little tube, and there is a connection to the safety valve outlet, so we can count the bubbles in this glass here. On the right side, there is step by step the steps of the methods. For example, if you have a spring-loaded safety valve and PSV valve, first you do the CDTP setting. Our CDTP setting is the initial audible discharge. And then we reduce the pressure of the set pressure, of the test pressure. The test pressure is, in overall, we can say the test pressure is 90% of your set pressure of your CDTP. Then we connect the bubble counting device with the outlet, and then we have waiting for calming time, and then we count the bubbles within the test time. And then we compare the actual and target values, the bubbles, and then the test is passed or failed here. And now there is a different to a PSV valve, an additional test we have to do if we are over 30 bar set pressure. Then we have to test also with 30% of your set pressure, because there we have a lower closing force. And then again, we have to have a look on actual and target value, and the test is passed or failed. In the next slide, there we see the difference between the API 5-7 and our LESER global standard. The API 5-7 goes directly with the test curve on with a test curve on the test pressure. This is a red line. This is 90% of your set pressure. Then we have a waiting time and the test duration time, and then we count here the bubbles and the test is failed or passed. And we, in our LESER global standard, go directly first to our set pressure. This means there we have the initial audible discharge. Then we go down to the test pressure. This is 90% of your set pressure. And then we have a waiting time and a test duration time where we count the bubbles. And why we go to the set pressure first? Because we say this is a realistic simulation of a safety valve behavior. The safety valve must open first, then the safety valve closed, and then we see if the safety valve is tight or not. And this we want to do now in our LESER chat room. Now we see here test bench. On the test bench is the API valve 1 to 2 inches. And here you see the manometer. Then I have here the bubble counting device. There, this is what I mentioned before. We have a water glass here, and we have a defined inner diameter of the tubing here. We have a defined diameter, or we have a defined water heat here, and so we have a defined bubble volume. Here you see it has a connection. The tubing has a connection with this rubber plug, and this rubber plug goes into the outlet here. Now we do our first live demonstration for today. I want to explain you the bubble counting method here. First, I'm increasing the pressure to our set pressure. Our set pressure is 3.5 bar G. If you see, if you see a little bit where is our initial audible discharge, I connected first, but be careful on your test bench. Do it on the other way. If I show you before, first go on initial audible discharge, and then after this, you go in with your rubber plug here. So now I go increasing the pressure up to 3.5 bar G. Now I reach the set pressure, and here we hear the see the initial audible discharge. And now we go a little bit near on the manometer here on this side. Here you see now I'm under 3.5 because the safety valve open on his set pressure, and yes, it is discharging. So now I go on the test pressure. The test pressure is 90% of our CDTP here. So I go directly on 3.15 bar G. Now I reach the test pressure. Now we have a waiting time, and then we count the bubbles. And for this, I will connect my tablet, and then we have a look into the water glass here. 1 second, please. Now I'm connected. I opened my camera. And now you see I'm live in the LESER chat room. And behind me here stands my team, Iris Nachtigall and Philip. And now we're counting the bubbles here. We have to wait. There is a first bubble, and now we count for 10 seconds up to LESER global standards. 1 second, the connection. I do it again. Hope you see me again now. I open the camera again, and we see here our first bubble is coming. And then we have the test time of 10 seconds up to LESER global standard. 4, 3, 2, 1, 0. So we see here we have a metal to metal sealing and no bubble in 10 seconds. So it is very tight, this API valve. And what is here, what stands behind this is that our name for this is LESER nano tightness. And for LESER nano tightness, it is very important. The material, for example, the structure of the tightness area here is important, and the hardness. And LESER invests millions of euros for special lapping machines, and so we called it LESER nano tightness. And here you see for a metal to metal sealing, we have 0 bubble in this case in 10 seconds, so it is very tight. Yes, this was our first live demonstration, and now I want to go on other safety valve. It is also the API model, but in the next case, we have the disk with the O-ring. And there must be 0 bubbles for the next test. Now the pressure is down. And one second, please. And now we use API valve. This is the same type now, and we use it, but we use now O-ring. One second, please. Now I must fix it, and then I finished. So now we have not changed the type. We have changed the disk. Now we have an API valve, 1 to 2 inches here with O-ring disk. So we do the same test. I increase the pressure on the cold differential test pressure. This is your test pressure for setting the set pressure here on the test bench. This is the same, 3.5 bar G. Now I have the first bubbles here. And now we're going directly again on the manometer here. And we see the set pressure. And now I reduce it to our test pressure. This is 90% of our set pressure. I go down on 3.15. This is here. I stop it. And now we have a look again on the bubbles. I connect my tablet. Now you see my tablet. I open the camera again. And we're going directly to the water glass here. And we see the safety valve is 100% tight because we used here a disc, a O-ring disc. So this was our first two live tests here. You see the bubble counting methods for API valve with a metal-to-metal sealing. In this case here, we have 0 bubbles in 10 seconds. We have to look into the API 5 to 7 there, and there stands the bubbles per minute. And LESER nano tightness, I explain in some seconds what this means in detail. So I reduce the pressure again. And now we are talking about the next topic. The next topic for today is body tightness. This was the functional tightness. Now we are going directly to the body tightness. First, we have a look into the presentation again. Here we see the LESER nano tightness, compare it with our LESER global standard and the API 5 to 7. You see for our API valve here in the LESER shed room on the test bench, we are in this area of 0.1 up to 69 bar with our 3.5 bar G. And then we have a look on the right side. We are equal or smaller than 18 millimeter D0. So for the LESER global standard, we have 20 bubbles. This is the half of our API regulation 5 to 7. Let's say 40 bubbles in 1 minute are allowed. So we have a half of the leakage of for the LESER standard, for the LESER global standard. And you see here in our case, we have a metal-to-metal sealing, and there was 0 bubbles in 10 seconds. So it was better than what we see here. In the next slide, there we see how to do the bubble tightness overview here. We have the back seat tightness. At LESER also called tightness toward the outside. We have testing the pressure bearing, say it's only for PSV valves. And we have the testing of the pressure bearing body. In the next slide, you see how it works for different designs. If you have a compact performance on the left side, it is important to spray with a liquid spray to see some bubbles or not to the inlet body or outlet adapter to the outlet body here. And there is a connection to from the body to the bonnet and from the bonnet to the cap. And if you have a balanced bellow, we see it on the next slide. There is one example a little bit later what it is mentioned for a balanced bellow design. Here it is important step by step. First, we have the setting of the CDTP. Then we have the test of the seat tightness. The test of the seat tightness you see before, for example, with the bubble counting methods. Then we going with the safety valve on the outlet and have a defined test pressure. The test pressure is 1.1 multiplied by the outlet pressure class or 6 bar. The lower value applies here. And then we have to spray with our leakage spray the connections. This was the connection I show you in the slide before. And then we have a look if there are no bubbles, and then the test is passed. And if we see bubbles, then the test is failed. And in the next slide, there is again the explanation of the balanced bellow design. And you have to form a bubble through the control hole of the bonnet here. And so you see if the balanced bellow design is tight up to the bonnet. And now we're doing here a live test of the body tightness with the same API model. I have to switch it now on the outlet. One second, please. And now I'm going on the outlet. Yes, it is in the middle. And now I fix it. So our first step was to set the CDTP setting. Then we do the seat tightness test. This was with the bubble counting methods here. And now we are doing the test, the tightness to the outside. And for this we use here this API model. So. Now I've connected, and now we're going to the set pressure, to the test pressure, and the test pressure in this case to have a look on some on the body tightness test. We're going directly on 6 bar G, and keep in mind here I don't reach the 6 bar G because I'm using here the control air from the laser chat room. It's going around about 5.5 bar G. But for the test, it is important to go on 6 bar G here. Now you see here, the pressure is increasing. And now I'm around 5.5 bar G. And now we do the body tightness test. We have to spray the connections between the body and the bonnet and the cap, and have to look if there are some bubbles or not. Here we see no bubbles. Then the connection from the cap and the bonnet. You see again, no bubbles. And then have a look on the screw here again with some liquid spray, and there are no bubbles. And now the test of the body tightness is passed. Now I have to show you a different safety valve, the pilot operated safety valve. There we must know some other test parts here. I reduce the pressure again. Pressure's down now. This was the body tightness test for the API valve. And now I want to explain where's the difference to the pilot operated safety valve. Here we see the pilot operated safety valve, the modulate action, and have a look on the first step was to set on the CDTP. Then we have to do the seat tightness test. This is in this case here the same. We do the bubble counting methods. And for the bubble counting methods, you go directly on the test pressure, and the test pressure was 90% of your set pressure. And here is now important, there is a connection, the tubing from the inlet of the pilot operated safety valve to the pilot. And this tubing we have to spray with liquid spray and have a look on if there are some bubbles or not. There is a difference to a spring-loaded safety valve here, the API model before. And now there is the same method here. We're going directly on the outlet. 1 second, I have to fix it. Now we have fixed it, and now we are going to the test pressure. This is again 6 bar. I increase the pressure. Now we are around 6 bar. Keep in mind here in the laser chat room for the control air, I have a little bit lower on 5.5 here in this case. And now we have to do some other parts. Here you see now we have the top plate, a connection to the body. This is to spray with our liquid spray here and have to look if there are some bubbles or not. From my side, the same. We see no bubbles, and there is a connection from the top plate to the pilot operated, to the pilot here. We have to spray it again on this connection. See, there are no bubbles. From my side, the same. No bubbles. And then there is some other step, you know, from the second laser training break, the function of the pilot operated safety valve. The pilot operated safety valve, here we have a backflow preventer, and we have to look if this backflow preventer works. And we see the safety valve, the pilot operated safety valve must tight to the inlet here. So we do a bubble in front of the inlet now. We formed a bubble. Now I formed the bubble, and we see there is no leakage, so the safety valve, the pilot operated safety valve here is tight from the outlet to the inlet, and the backflow preventer do its job. This was our laser training break for today. You learned something about the different definitions of tightness, the body tightness, and this was a test of a body tightness. And you learn the other definition of seat tightness. Have a look into the API 527 and the laser global standard with nano tightness. And if you have not registered for the next session in 1 week, it is in the next week, then do it now. There we are talking about inlet pressure loss, and we show some live demonstration with the shattering. For this stands our name Laser Chat Room here. And if you have any technical questions, please write me directly directly an email to my email address. This is erding.m@leser.com. Have a nice day and see you in the next session.